Okay, so today we have a seminar come from Professor Jen Bay about wall models of turbulent flow via scientific multi-agent reinforced learning. And to me, it's very nice that Jen has accepted. I know Jen from a lot of years ago on some of my visits to Stanford. She at the moment was like a PhD student of Parvis, working on a lot of things, no? Novel circuit models, basic analysis, no, of the flow. And right now it's one of, in my opinion, of the more interesting young researchers. And now it's already professor. It's doing very interesting things, both on analysis of modeling. And today she will be talking about how to use reinforced learning to build a novel wall model. Okay, so I'm very glad that you accepted, and I think it will be very interesting.
Great. Thanks for the introduction and invitation to talk here to Oriol and Bernard. So today I'll be talking about wall models for turbulent flows using this method called scientific multi-agent reinforcement learning. I want to acknowledge the funding sources that are listed here and also the Stanford CTR summer program, which where this work was also presented as well, part of it at least. I also wanted to acknowledge my collaborators from this work. So Dizu from Caltech has been working mostly on extending this model to separated flows. Kevin Griffin, Michael Whitmore were students at Stanford helping us out at the CTR summer program. Madi and Aurelian are at Aarhus University, and Xiang from Penn State and Petros from Harvard. They were all, big parts in getting this work started and up and running as well. So I want to acknowledge them. This is the outline for today's talk. I'll go into a brief introduction. I know everyone is more or less familiar with the topic, but I'll start with, what is turbulence and why is it important to model turbulence? I'll talk a little bit about prior approaches of wall modeling. And then I'll go into our approach, which is using this reinforcement learning for wall modeling. I'll start with a very canonical channel flow case and talk about how to mitigate effects of Reynolds number when we're doing wall modeling, and then move on to smooth body separation and look at, effects of not just separation, but just effects of adverse pressure gradient, favorable pressure gradient, and separation as well. And then I'll summarize in the end. So turbulence, at least in the US, when you say turbulence to a normal person, this is kind of the picture that they think about is just airplane turbulence. But, turbulence is quite ubiquitous. It's everywhere. So if you see blood pumping in a heart, this is quite turbulent flow. When you have, you're mixing milk to your coffee, this is also a turbulent phenomenon. When you look at this white water, this is also an example of turbulence. And on a much larger scale, this is the atmosphere of Jupiter, and you can see turbulence here as well. So it has a lot of applications. It has a lot of natural occurrences. And more formally, we can define it as a chaotic and disorganized motion of a fluid. And typically, we define this using a non-dimensional number called Reynolds number, which is the scale of velocity times length scale divided by viscosity. And when this number gets really, really large, you get turbulent flows. Another way to think about it is, large scale, the ratio between large scales to small scales. So if you have a large scale separation between the small scales of motions in the flow and the large scales, usually defined by some geometry, then you get a turbulent flow. So these are when kind of turbulent flows occur. Like I said, there's a lot of applications in engineering and physical sciences where you have examples of turbulence. For example, when you have oil moving through a pipe, when you have an airplane, atmospheric flows are turbulent, and some biological flows, even at a very small scale, can become turbulent. So again, a lot of applications and examples of turbulence around us. More formally, to kind of motivate the topic of turbulence, we can look at some numbers. So 25% of the energy used in industry is spent moving fluids or moving objects through fluids. And 25% of that energy is dissipated close to walls. So wall-bounded turbulence in particular, out of all turbulence, is responsible for about 5% of the CO2 dumped into the atmosphere. So it seems like by targeting wall turbulence and learning to somehow mitigate it or reduce its effects, we can kind of reduce a lot of the CO2 that's dumped into the atmosphere and make more efficient airplanes, for example. On the other hand, from a more physical standpoint, Richard Feynman famously said that turbulence is the most important unsolved problem of classical physics. So, it is still unsolved. There has been, decades upon decades of research, but still, it still is a very important and difficult problem to solve. So, from a more intellectual point of view, it's still an interesting problem. So let's look at how we typically do simulations of high Reynolds number flows. So like I said, Reynolds number is the ratio between large scales and small scales. And once this gets big, you get turbulent flows, right? So let's look at what this means. Here on the left, I have a plot of length scales as a function of the distance away from the wall. So the x-axis is the distance away from the wall, and the y-axis is the length scale. The red line indicates the shear length scale given by the inverse of the shear, and this indicates the large scales. And the black line here is the Kolmogorov length scale, which is the small scales. So you can see that both of them grow as you go away from the wall. So this direction is away from the wall. But the large scales grow a lot faster and the small scales grow a lot slower. And away from the wall, you get a large scale separation. When you resolve all of these scales of motion, so you resolve all the small scales and you have a domain large enough for the large scales, this is called direct numerical simulation. And in order to do that, you would need a grid that is very, very fine everywhere. And turns out, in terms of Reynolds number dependency, this computational cost grows on the order of Reynolds number to the power of 2.6, which means it grows very, very fast. And considering the fact that, typical real world engineering applications have Reynolds number on the order of 10 to the 5 and 10 to the 6, this is a very, very large number. Just to put this into perspective, in order to simulate an airplane wing, using DNS, you would actually need on the order of 100 years or more to get this simulation done using the largest supercomputer that we have right now, which is definitely not feasible, especially for engineering applications. And if you want to do design using simulations. So this is not feasible. So then, the next step of approach in kind of trying to reduce this computational cost is to incorporate modeling. By modeling, you can reduce some of the computational cost. There is some loss in fidelity, but with a good model, the hope is that we can kind of fill in that gap. So the idea of the large eddy simulation is, instead of resolving these small scales, which cause the grid resolution to be very, very fine everywhere, we're going to try to model these small scales once we have this big separate scale separation. So away from the wall, these subgrid scale models for large eddy simulations work quite well, and that's kind of the idea. By doing that, you can coarsen the grid as you go away from the wall. This is the idea of large eddy simulation, or wall resolved large eddy simulation, we'll call it for this. But you'll notice that you still have a very fine mesh close to the wall. So this reduces the cost, so it becomes on the order of Reynolds number to the power of 1.9. Still, this is not quite enough for everyday applications to large industry related problems. And the issue is because of this region right here, where you still need a very fine resolution, even in LES. Here you see that you don't have much of a scale separation. Physics are quite different because of the presence of the wall. And because of that, you can't use the same subgrid scale model close to this and assume that the flow will be modeled correctly. So you need a separate model for this region, which we call it the wall model, because it's modeling what the near wall effects. So here you need to model both what the large and the small scales are doing. And if you do that, you would get a grid that is coarse kind of everywhere. And the hope is that this is either Reynolds number independent, or at least at the very least, at the very most, linearly dependent on Reynolds number. So these are the type of simulations that you can actually apply on actual aircrafts, as you can see on the right. So this is the flow field you get from doing wall modeled LES of an actual plane. So quite impressive. Just to give you some kind of real world background on this. So there's this idea of certification by analysis, where you can use analysis-based means, including simulations, to test compliance or of airplane and engine certification. And this is a chart that I pulled from the STAR CCM website, just to give you an idea of how cheap it is to do a simulation if you do it kind of well with a good model. Obviously, you would need a good model for it, but compared to experiments or flight testing, this becomes a lot cheaper. So having a great model can, open doors for using CFD experiments to do these sort of things in a much faster and cheaper way. Okay, so now that I've kind of explained what wall modeling is, well, at least like the motivation behind wall modeling, I'll go into a bit more detail about what wall modeling is and how it's typically done. So the idea for wall model LES, like I said, is to model the near wall region. And the idea is to bypass the near wall physics and supply the wall shear stress directly, because it turns out that the wall shear stress is the most important quantity that you can get out of this near wall region. And if you can supply that through different means correctly, you get more or less a good prediction in the statistics. So in wall model LES, we typically have a coarse simulation grid. So something like you see in the blue here. You take some velocity and some information from the grid point away from the wall, like fluid velocity, viscosity, density, things like that. You feed that into the wall model. The hope is that the wall model will spit out the wall shear stress, which I'm denoting as tau wall, and you apply that as some sort of boundary condition back to the coarse simulation grid, which allows the flow to basically model that near wall region and get that information from the wall model instead of resolving that region. So this is the idea. In the past, people have developed good wall models. So there are state-of-the-art wall models that are being used right now that are simple to use, and most of them rely heavily on this idea of the law of the wall. So here we have a typical velocity profile when you have a flat plate. So you would have the viscous sublayer where the velocity is linearly correlated with the distance to the wall. You'll have a transition layer, then you'll have a log layer where the velocity follows this log law, where kappa and b are empirical coefficients that were computed using experiments. So people will use this, and one of the first models that were actually developed in the 70s is called the algebraic wall model. And the idea is that you assume that this log law exists everywhere, and you solve for the wall shear stress. So basically U tau is a proxy for the wall shear stress, which gives you the relationship that you want. And this works quite well. It's very simple to solve, and is still used quite widely. Obviously, if you have a grid point in the viscous sublayer, this wouldn't work because it assumes everything is a log law, and it doesn't really take into account this viscous sublayer. So people have kind of improved upon that and came up with this random space wall model, which typically people call equilibrium wall model, where it'll take into account the viscous sublayer as well. So this red line is then modeled by solving this simple ODE. Now, both models take extensive advantage of the knowledge of these two coefficients, kappa and b. So you have here kappa and b explicitly. Here in this model, you have kappa and a, which is tuned to match the coefficient b that you would get for the log law. So this is very much tuned to get this red or blue profile, if you'd look at it that way. The problem is with these state-of-the-art wall models is that a lot of the different flows that you would see don't really adhere to that law of the wall, especially if you have complex geometry and things like pressure gradient effects. You will see that the velocity profiles start deviating from this typical log law. So here I have an example where, here on the bottom in this red, you have a typical zero pressure gradient effect flow, where you can see that it adheres more or less to this log law. But as you start, increasing your adverse pressure gradient effects, you would see that it starts deviating farther and farther away from this dashed line. And you'll have this shift that occurs that you cannot really model using the law of the wall. If you were to try to model something like this, you would need to either recalibrate your wall model values for all the pressure gradients and Reynolds numbers that you're doing, which is not really feasible. People kind of just use the typical wall model regardless, and that's where the discrepancies typically happen. Similar thing with roughness, textures, porosity. You would see again a shift in this log law, typically just the log law y-intercept. So the slope stays more or less similar, but you would see this shift. So if you have a very complex rough wall where it's not a single roughness, it would be a bit more difficult to simulate using these state-of-the-art wall models. So that's where kind of machine learning could help, and that was kind of my idea. I'm going to briefly talk about supervised learning in wall models because a lot of people have done, well, some people have done it, and I think it's a great idea. But the issue with supervised learning that I see for wall models is just the amount of data that you would need. So here on the top, I have an example from Yang et al. In 2019. You can see that using supervised learning, you can do quite well in terms of getting the log law correct. But again, if you were to look at all of these different type of flows that you need to adjust your model for, you would need a lot of DNS data, which sometimes is not present. These canonical flows, you have a lot more data for, but for the complex flows, you wouldn't have so much data. So just generating that data becomes very taxing. Also, there is this known of, there's the that there's no direct coupling between LES and DNS. So in these supervised learning cases, a lot of the times what people do they would take this high fidelity DNS data, they would filter it down and use it as a proxy for your LES data. But it's well known that filtered DNS and LES are not quite exactly the same. So by doing this, you get a model that works great a priori, but then once you start applying it, you get some problems. So that's kind of the shortcomings of supervised learning that I've seen in wall models. So with that as our introduction, I'll move on now to kind of our approach, which is using reinforcement learning for wall modeling. So going back to this picture, the schematic of wall modeling. So you have this core simulation grid, you take some information from the off-wall location, you feed it into the wall model, and you get the wall shear stress back. This is a very good depiction or a cycle that you would see actually in reinforcement learning. So in reinforcement learning, we would have to relabel some of these things. So our course grid simulation becomes the environment. The information that we take from the environment are states. The wall model is represented by an agent, and then the agent performs an action on the environment. And on top of that, we would need a reward on how the action is doing during the training process. So the objective of reinforcement learning is to find an optimal policy that maximizes this long-term reward. So you do training by assessing this reward integrated in time, which actually solves one of the problems that are raised for supervised learning. Because you're integrating the reward in time, you actually see this coupled effect between LES and the learned model. So not only is the model trained for single step, not just a single step, but it's designed to work in a long-term basis. Okay, so having this diagram in mind, I'm going to go through the individual components for the wall modeling part and explain why we chose the way that we chose it to be. So we're going to look at these three things: the reward, the state, and the action, because these are the ones that are important in training the wall model. The environment is just the large eddy simulation, so this is kind of a given. So first, let's start about action. So reinforcement learning is great at control problems, mostly because, again, it sees what's happening and then it turns a knob. It sees what's happening again and then it turns a knob. So you can kind of think of it as if you were, trying to, tune something. You would turn a knob, you'll press a key, you'll turn a knob, press a key, and try to match that. So that's kind of what reinforcement learning is doing. So instead of posing it as just like predict the correct wall shear stress, we've posed it as a control problem where we look at it as the control of wall shear stress. So what it would do, it would take the wall shear stress at a previous time step, apply some control mechanism where we give it some range. This range is actually, turns out it's not important if you do the training well. It mostly depends on the size of the time step. And then you get the new wall shear stress at the next time step. So it becomes like turning a knob a little bit. So you either increase or decrease the wall shear stress at a given time step. For the reward, this looks like a very complex equation, but the idea is that we have some calculation of an improvement compared to the last step. So we need the true wall shear stress for the training purposes for the reward. And then we also give it a bonus if the error is less than 1%, because once you've improved it to a certain degree, you cannot improve it anymore. So we added this bonus term to make sure that you stayed in this correct region. For the state, we've tried several combinations, and we'll go through it one by one. But for model one, the first model, we're going to start with a very simple, naive formulation. For this first state, we're going to use the velocity, and the second state, we're going to use the wall normal locations that are normalized using the modeled quantities. So again, going back to this idea of the existence of the log law, so we know that there's some relationship between y plus and u plus, and we're going to try to use that in our model. And we know that this model, this law is more or less Reynolds number independent for flat plate flows. So that's what we're going to try to do. So very simple model: velocity, wall normal location. These quantities that are here are modeled quantities. So there's no information that we're taking from the ground truth other than when we're computing the reward. So this is our first model. And the idea is that if you had a point here that was above the log law, somehow through the reward system, the model would learn that you would need to apply an action to increase the wall shear stress so that you could move this point down and be closer to the log law. So moving on to training. So for training, we used a channel flow at Reynolds number of 2,000, 4,000, and 8,000. The good thing about channel flow is that the true wall shear stress is kind of known a priori from the pressure gradient. So we didn't really need DNS data, but these are Reynolds numbers that actually have corresponding DNS data. So that was also good. For the simulation, we used a LES with the AMD subgrid scale model. The grid resolutions was about 0.1 delta, so there were 20 points along this channel half height. The code that we were using is a second order finite difference code in space and a RK3 scheme in time, very generic. For the reinforcement learning, what we used was, so we have two planes, right? We have the wall where the action is being applied, and then we have the plane off the wall where the states are being collected. For the reinforcement learning, each of these grid points were agents that were training a single policy. So we had these multiple agents training a single policy, and that's where the term multi-agent comes from. So we have multiple agents on the domain training a single policy. We used a library called Smarties with a policy called VRacer, which is a off policy training for reinforcement learning. The details of the RNN that we used are here, although we didn't see that much dependency on the architecture itself. So with this training, we just wanted to see what the model has learned. And a really good way to see that for reinforcement learning is to plot this thing that I'm calling the action state map. So here in this plot, I have the first state, that is U plus on the y-axis, the second state on the x-axis, and in colors, I'm showing the PDF of regions where we have an action that is greater than 1, and PDF of regions where the action that is less than 1. So this is parts where we're decreasing the wall shear stress, and this is the part where we're increasing the wall shear stress. And you can see that they're very well divided. And in particular, it's divided by this log law, which we never really supplied in the training process. So the model does a good job in figuring out when to increase and when to decrease the wall shear stress, at least based on what we observe from the trained model. So let's see this in action. Let's see how this does. And to do that, we're doing testing. We're looking at Reynolds numbers that we haven't really trained on. So there's one Reynolds number that is in between the training sets. And then there are Reynolds numbers that are much higher. Same LES details. And this is what we get. So here we have a plot where we show the Reynolds number on the x-axis and the error in the y-axis. You can see that the errors are quite low for these low Reynolds number cases that are close to the Reynolds numbers that we trained on. But then as we increase in Reynolds number, you see this significant error that occurs as you go up in Reynolds number. So why is that? If you remember from this, this law of the wall, so you'll see that the range of y pluses, so the second state that we use, the range of these values that we gathered from testing is in this very small band in the log law. And you'll see that when we test, we increase the Reynolds number without increasing the grid resolution. So you would see that this is the region of y pluses that is occurring in the test data. So when we go to these high Reynolds numbers, we're actually showing the model values of a state that it's never seen before. And because of that, you accumulate this error. Again, machine learning is very good at interpolating, but it's very bad at extrapolating. So if you train in a very different data set, it's not going to do very well. So one way to mitigate that is to increase or do a grid refinement. So decrease the grid resolution, or sorry, increase the grid resolution as you increase Reynolds number, so that the testing and the training regions for y plus stay similar. And by doing grid refinement, you actually get a lot better improvement in the predictions. So, this is something, but it's not really a feasible model because, first of all, in real world applications, you cannot predict the local Reynolds number prior to the simulation. So having a very short range of Reynolds numbers where this model would work in is not really ideal. So again, it works for some Reynolds numbers, but it doesn't. And it's because of the choice of state that we've made. So to kind of mitigate this, we've thought, what is something that is more universal, something that doesn't depend on Reynolds number in terms of the ranges of the states that we would see. So again, we went back to this idea of the log law, and we thought that, well, kappa and b are considered constants. So let's try to kind of figure out our model around that. So the first state that we chose is kind of this log law slope. And we compute that using instantaneous quantities. So it's not like we're actually showing the real kappa. We just use this equation right here to compute the slope of the instantaneous log law using our velocity and velocity gradient and wall normal distance. So this is the proxy for our log law slope. It's a misnomer calling it a log law slope, but we're calling it that just to show you the link between what we're computing and what is actually present in the log law. For the second state, we're using the log law intercept. So again, this is the proxy for this. So we have y plus, and then this quantity is what we put here, and then times the log of the ym. So again, these are all computed from the instantaneous values and the modeled wall shear stress. But these are proxies for the log law slope and intercept. And again, here the hope is that if we know, the slope and the intercept at some time, the action will be able to adjust the value correctly to the correct place on the log law. So here's the action state map for this case. It's a bit more difficult to interpret because before we had actual physical quantities like u plus and y plus, and we knew exactly where the division should happen. But here now we have the proxy for 1 over kappa and b. However, one good thing is that it is still relatively well divided. So you see a division between when you have to increase the wall shear stress and when you have to decrease the wall shear stress. So it seems like the model has at least learned something out of this. When we test this, so just going back a few slides, here the errors were on the order of, maybe 60% when you get to the highest Reynolds number that we tested. Here, the errors are fairly low, so we have about maybe 4%, which is quite low. Still, the equilibrium wall model will be mostly on this line, so it's not really an improvement on the existing models, but we're still doing much better than the first model. And here are the mean velocity profile. So you'll see that, this has the 4% error in the wall shear stress gives you this deviation that you see here for the largest Reynolds number, which is not ideal. So you see again, this kind of shift. And the reason for this discrepancy, so again, this model is a lot better than the first model, but it seems like it has some issues. And one of the reasons is because this line that divides the increase and decrease in wall shear stress, actually it depends on the location of the matching location. So for low Reynolds numbers, it's easier to pick points that are kind of in this range, from about 100 plus units to 500 plus units. But as you go higher in Reynolds number, you start tilting this what we call the neutral line up. So this function, this neutral line, becomes a function of Reynolds number if you keep the grid resolution constant, which is causing that issue. So when you have a grid resolution around y plus of where the matching locations is around y plus of 500, you have no issues because the model is doing great in this region. If you have a small deviation from that, that's also fine. But as you get bigger and bigger, you get a shift in this direction, and the model that you trained no longer has the correct neutral line compared to the Reynolds number that you're training. So again, a similar problem. It's more subtle because the shift is not as intense as that issue of having a completely different training and testing values, but nonetheless it becomes an issue. So that's where we came up with this adjusted log law model. This is a model that I've worked on with people from our house and Penn State. And basically, we've tried to make sure that neutral line stayed constant regardless of where the Reynolds number is. So here we've reintroduced this true kappa in the model, which is not ideal, but it seems like at least the slope of the log law stays pretty constant regardless of flow type. So we thought this was, a compromise that we could make. So this is, again, now the proxy for the log law slope. And then this is our log law intercept. So by doing that, what we did was we adjusted that neutral line that was shifting for different Reynolds numbers to a single line, which means that there's a single policy that will work for any type of matching location that you would throw at the wall model. And that gives us a really good result. So here we have Reynolds numbers up to 10 to the 10. There's still some small deviation at very low Reynolds numbers, but because typically wall models are geared for very high Reynolds number flows, we were more interested in this region, and it seems like it performs, well up to extremely high Reynolds numbers. So, by fixing that state to incorporate this knowledge about the flow, you can do much better in terms of the predictions. So that was our kind of understanding from this very canonical channel flow example. So we looked at the effect of Reynolds number and how changing the states would give you a lot. Some states will give you a lot better prediction regardless of Reynolds number, and some states wouldn't do so well. So kind of knowing this, we went to target this idea of smooth body separation and effects of separation using wall models. So the first case that we're using essentially to train the model is this flow over periodic hills. It's a very simple case because it is an internal flow. You have a wall on the top, wall on the bottom, and it's periodic. So the benefit of this is that you don't have to tune inflow conditions or outflow conditions, and you have a very statistically steady state along this periodic hill. So we used a second order finite volume code for this. it's an unstructured mesh code, but we've used kind of this very simple hexagonal mesh. We use the dynamic Smugglensky model for the subgrid scale model. And again, there's a periodic condition in the streamwise and spanwise direction, which makes it a bit easier to train. The Reynolds number for this based on the hill height is about 10,000, which we have extensive DNS and wall-resolved LES data for. And the grid resolution that we use for the wall-modeled LES is quite coarse with uniformly distributed points using this grid resolution. Same library was used for reinforcement learning, same architecture. And basically, we kept most of the things same. So the action is more or less the same. The reward is more or less the same as the channel flow case. The only thing we added were extra information apart from the log law slope and the log law intercept. We've also added some information about pressure gradient and shear strain to account for the additional intricacies of having a pressure gradient driven flow. So we've added these two states. So now we have 4 states. And the action and the reward stays more or less the same. So here are the results of this trained case. So in black kind of symbols, we have the DNS data. This is the CF. So you have a separation where you have the CF below 0, and then you have this highly favorable pressure gradient region where you have this peak. In the blue, we have the results from the equilibrium wall model, which is the standard wall model that people tend to use. So you'll note that they have a very small separation bubble, a lot smaller than the true separation bubble. And the favorable pressure gradient region is very much reduced. So you have a peak that is a lot lower than the true peak. In the red and green, we have our trained model, one with the same mesh resolution that we've used and one with a coarser mesh. You'll see that here in the separated region, it still does some funky things, so it's not quite perfect. Still, it predicts a much larger separation bubble than the equilibrium wall model. And even the kind of the trends seem to be similar, although the magnitudes are a bit off. But it does a lot better, for example, in this favorable pressure gradient region where it can actually predict this peak quite well. So this was very encouraging as our first pass. In terms of the separation bubble size, you can see from the streamlines that the R model on top has a much bigger separation bubble than the equilibrium wall model, and that size is kind of comparable to this result from the wall-resolved LES that we have. We've also tested this model for higher Reynolds numbers. So there's some results for higher Reynolds numbers. And as you can see, our model in green and red, again, predicts the favorable pressure gradient peak quite well, even at these higher Reynolds numbers. And the separation bubble is also predicted relatively well, at least compared to the equilibrium wall model, which is a good sign. So this was the example of the periodic kill. Going back to see what we can extract out of the wall model, we haven't really done this extensively yet, but we decided to look at the state action map just to see if we can kind of discern something out of what we've learned. So we looked at kind of the state action maps for 3 different locations along the simulation. And you can see that, even if the 2 states are same, the values differ quite widely in the 3 different locations that we're looking at. But similar to the channel flow case, you can see a clear separation in the regions where we're increasing the wall shear stress and the regions where we're decreasing the wall shear stress. So it seems like the model is definitely learning to distinguish something. And if we were able to explicitly write this separation line out, hopefully we can kind of recover what an analytic form of this wall model might look like. So this is kind of our next steps. instead of stopping at a single geometry, we also wanted to see what the model can do in a different geometry. So we applied this model to a Gaussian bump. We've looked at 3 different resolutions for this. We applied the model that was trained from the periodic hill case. So we didn't retrain this model for a more complex geometry. We were hoping that the model that was trained for a simpler geometry can work for this complex geometry. So this is kind of the simulation. And this is the skin friction. So here, the blue, again, is the equilibrium wall model. The red is our model. For the closest model, both don't do quite well. So they're more or less similar in what they're doing. But for the medium and fine mesh, you can see that our model predicts this favorable pressure gradient peak quite well prior to the bump. And the separation bubble, even though it's almost non-existent, there exists separation, whereas the equilibrium wall model case doesn't. Now, if we go to finer resolutions, because even our finest mesh here is considered pretty coarse in this simulation, we don't know exactly what will happen, but that's kind of in the works as well. But we're encouraged that at least the model seems to work in different geometries, even though it was trained for the periodic hill case. So let me just summarize my talk. So I've talked about this multi-agent reinforcement learning as a tool to discover more models for LES. It's a data efficient way of training because we're training on a LES grid, on a wall-modeled LES grid already. So we're not running a DNS. If you calculate this, even if you have to do tens of thousands of simulations to do these training, it's a lot more efficient than gathering DNS data to do supervised learning. Also, there's a direct coupling between the model and the learning process because you're learning in the environment where the model will be applied, unlike supervised learning. So this is a pretty good way to do model developments for wall models. And we've shown that at least for flat plates, we were able to predict the wall shear stress for different Reynolds numbers. And we've tried to extend this model to pressure gradient flows using the periodic hill configuration. Something that we've learned from this process is that the choice of the state is very, very important in the generalizability of models. The actions and the reward also play a role, but it seems like the state, it really makes or breaks the model. So in order to make sure that in future works that you have a generalizable model, it's really important to think about this state space and how this changes when you change a certain variable. So it seems like if you can get a single state space, it becomes a lot easier to train a model that is easily extendable to different configurations. So with that, I'll take any question. I think I have a page on all the publications that are related to this work. So we have the 2 papers here about the channel flow case, the first 2 models, and then the 3rd model. We have the periodic hill training case, and then the testing on the Gaussian bump here, both in the AIAA aviation paper and the summer program proceeding. So with that, I'll end the talk and take any questions that you might have.